Hi, good afternoon. I'm Ramesh and I will be talking about the convective heat transfer assignment 2. For me, there were three problems and we'll go one by one. The problem one description is that, as you can see in this illustration, there is a metal block with high thermal conductivity and there is a vessel over it and there is a air gap with over it air gap between the vessel and the heat block. So the heat block is maintained at 300 Kelvin and the vessel is the bottom part of the vessel is maintained at 243 Kelvin. So the air gap is given as 0.03 meters and the one thing we are trying to change is the air pressure in the insulating layer. That is changed from 0.1 bar to 0.05 and subsequently 0.01 bar. So that is the description. And the way I approach this problem is since the assumptions made are like the heat transfer due to radiation is neglected and properties of air change with pressure and are estimated based on the ideal gas law. So and the layer is thin that the temperature gradient is same across the area. So that is also assumed. So since for the conduction heat transfer rate, the parameter that will change is the thermal conductivity, and I assume that it will vary linearly with the pressure. So I got this expression from the AAP data book. So based on this calculation, the conductive heat transfer rate can be calculated. And for the convection heat transfer rate, so I calculated the Rayleigh number with the help of MATLAB code, and the results are like in the order of 10 power 4. So it says that the convection is starting to dominate the heat transfer rate. So the total heat transfer rate will be the sum of conduction plus convection. So for the Nusselt number correlations, uh, I used the uh, for the Nusselt number correlations, I used expression from the Incropera textbook, that is C into RA power n, and based on the calculations, these are the values I got. So we will discuss about the MATLAB code. So these are the constants given as part of the input, and this is the pressure we are trying to measure: 0.1 bar, 0.05 bar, 0.01 bar, and the loop calculates. Loop takes in pressure as input and calculates the density and thermal conductivity for the calculation of conductive heat transfer coefficient, and the Nusselt number and Rayleigh number for the convection heat transfer coefficient. So, and the sum of these two will be the uh, total heat transfer coefficient. So, based on the inputs and calculation, we got these values, and the interpretation is as we reduce the pressure from 0.1 bar to 0.05 and 0.01, the total heat transfer rate decreases. So moving on to the problem two, the problem two's description is, you can see from this illustration, there is a where there is a flow over a flat plate, and where should we place this trip wire? Essentially, the trip wire is like this earphone, maybe a wire, and to increase the turbulence so that it will increase the heat transfer rate over the plate. So the solution for this problem is I calculated the idea behind is this: the tripwire should be placed at exactly where the Reynolds number changes from laminar to turbulent, so that it further increases the turbulence and increases the heat transfer rate. So from the Nusselt number correlation for turbulent flows, so the value A should be minimized. It should be brought down to zero, so that the maximum Nusselt number can be achieved. The maximum Nusselt number says that there will be a larger heat transfer rate. So based on this calculation, I got the value for optimum Reynolds number is that 3159. And so the inference behind it is, if you substitute 3159 in the equation, you will get optimum A of minus 14. And so for placing the wire, since the length of the domain is not known, um we should I can't calculate the exact location of the plate, but we can roughly say that the location corresponding to where the Reynolds number is 3159 uh, should be the place where the tripping wire should be placed, so that it enhances the heat transfer from the plate. So moving on to the next problem. So this problem is related to the surface temperature, average surface temperature, and the convective heat transfer coefficient, convective local convection coefficient. So there is a plate with uniform heat flux given over it through this wire, and the ambient is air, and there is a flow with the velocity of 5 meter per second, and the length of the length of the plate is 1 meter. So there are three things we need to find. So the plate surface temperature, the local convection coefficient, and at the trailing edge of the plate, and the average surface temperature as part of the second subsection. And we should plot the surface temperature variation and heat H convection coefficient across this domain to visualize how this trend is looking like. So these are the assumptions for this problem. Like it is assumed to be steady state, and flow is turbulent, and there are no property changes on the plate or the fluid. So these are the properties taken from data books. So the flow is given as air. So the mean temperature is assumed to be 325 Kelvin, and kinematic viscosity and thermal conductivity and Prandtl number are taken from the data book for that temperature. So for the section E, we should calculate the surface temperature and heat transfer local convection coefficient at the location L, that is at 1 meter. So we can use this standard Fourier's law of formula. Q heat flux is equal to Hx L into Ts minus T infinity. And local convection coefficient for the turbulent flow is assumed to be, from this correlation we can get the Nusselt number, and subsequently we can calculate the Reynolds number as well as the convection coefficient, and plugging in these values back to it will give you the surface temperature at the tip of the uh, plate. So it is found to be 98.3 degrees Celsius. So these are all coded in MATLAB. And for the average surface temperature, we use the integral equation. Ts minus T infinity is equal to flux by length, integral 0 to L, 1 by NUX dx. NUX is given by this expression itself. And uh, through with the help of MATLAB, so the value is computed as 86.1 degrees Celsius. So this is the MATLAB code written for this problem. And the variation of TS and TH is plotted as part of the subsection C. So the left side is surface temperature in degree Celsius, and the right side is convection coefficient H. So this bottom is the length of the plate. So you can see there is a upward trend of surface temperature, and there is a downward trend of convection coefficient along the length of the plate. So this is because as we move along the plate, the heat transfer surface temperature increases due to the accumulation of heat transfer from the leading edge. So indicating more energy is absorbed by the plate as the air flows over it. And regarding the convection coefficient decrement, It is because due to the boundary layer thickness growth over the plate, making it difficult for the fluid to transfer heat. So it reduces the temperature gradient, and thus it is reducing. So the trends of TSS, surface temperature and heat convection coefficient, is like it is both are competing for competing, and one increases across the plate and the other one decreases across the plate. So yeah, thank you.